Okay, so the question's going to say, Mr. Sadler pulls his 20-kilogram daughter up a 30-degree snow hill.
Okay, what's the title?
Title's going to be test review. Is going to be the title. It's going to be that. If the rope is inclined 35 degrees to the sled, what force must Mr. Sadler exert to keep in equilibrium? Okay, this is a true story, okay? This happened this weekend. My daughter made a new friend on the street that lives 2 houses down. They decided to go tobogganing in my backyard. And I went to Mr. Sadler, that sounds like fun, and it was. The problem is this, though. My backyard looks like this, and guess what's at the bottom of the hill? A fence. That's good. So my kids maybe aren't the smartest in the world, okay, because they like to slide into a fence, but they're going to be good football players one day. That's the story now. That's not all. Right. So anyway, but that's the question. Now, one of the key words here for this is equilibrium. Can someone tell me, please? And we're going to use Spider-Man today. Anyone can go here. Brandon, what does equilibrium mean? F net equals 0. Okay. So all my forces. Okay, so that basically means all forces add to 0. Okay, now you may say, Mr. Sadler, it's just you pulling a kid up a hill. What's the other main force working other than Mr. Sadler's pulling up the hill? Gravity is going to be the main one. So I'm going to try and draw right now for you guys the diagram. I'll give you a second to finish writing. And I'll try and draw the diagram so you guys can understand how to draw these things. Once you understand how to draw them, you know, life's not too bad on these. It's just trivia, okay, right? But you got to get the first idea of gravity. Okay, I'm going to slowly, up to there almost. A bit almost. All right, here we go, guys. So, I'm going to ask people at random, starting with Caleb. Caleb, if you were drawing this diagram, what would be the very first thing you put on there, do you think?
Snow.
The snow, or the hill, or whatever you want to call it. So my hill is going to be 30 degrees. Now I'm going to draw 2 diagrams here today. So leave enough room on your page for the first, and I'm going to draw another one here down below. The second one is optional, okay, but I find it a lot easier and clear to do it. So there's 30 degrees. Straight down, yes, my hill is perfect. Well, it's actually more of a sinusoidal hill, but I'll leave it for right now, okay? Okay, stay with me. We're in chapter 2. By the time we get to chapter 6, we use a sinusoidal hill, okay? All right, Alan, what else can I put on this diagram?
The rope to the sled.
Yeah, rope to the sled. I'm also going to do one other thing before that. I think I'm going to put my daughter on first, and then I'll deal with the. So my daughter here is going to be a box, because that's all I can draw. And she's going to be 20 kilograms. Okay, but Callum said exactly right. So the way we're going to draw the rope to the box, when it says 35 degrees to the sled, what does that mean? I'll open this up to anybody here. Yeah, go ahead. Yeah. So what we're going to do, the rope, instead of going straight across, because I can't pull her, I'm a lot taller than my daughter is. Okay, my arm's sort of pointed out sort of like this. And we're going to go up 35 degrees. What's that? Okay, one other thing we need to put in there, probably 2 more things we need to put in there. Brad, is there anything else we need to put in there, do you think?
Yeah.
Okay, you know what that is? Okay. What else do we put in here? Now, we said over here the forces that we need here, right? What are the 2 forces that we're putting in? There's only 2 things working. Go ahead.
Gravity.
Gravity is 1, okay? So my force of gravity, I'm going to put straight down because it always goes downwards. Okay, Fg stands for the force of gravity. And it's always straight down. All right, Jason, there's one more force in this other than gravity. What is it? What else is me? Okay, so this is force of Sadler. Should I call force of Sadler? Is that too exceeded?
No,
Force of Sadler? Okay. I'm going to move this down a little bit because I don't want to have it. And I'm pulling like this. Force of Sadler.
Can I not just go on the same line as the 35?
It is the very same line as the 35 meters. If you want to just pull it, if you want to draw it right on top, I'm going to draw it separately just so we know what's going on, okay? All right, now this is the part that I'm going to do to save the people that have no idea what's going on in this question. We need to get the forces that are parallel and perpendicular to the hill. Okay, so what I'm going to do is I'm just going to redraw this so that instead of going like this, the hill is going to be flat. Okay, and this will hopefully help you to visualize things. If it doesn't, you can use the forces on the original diagram and that's fine. But I'm just going to spin this a little bit, sort of like this. Okay? So you see what we're doing now? Instead of the hill being angled, now the hill is going to be flat. So here's Ava. Does everyone see that? There's Ava. Now is instead of being up on the hill, now she's flat on the hill. Okay, the only thing we need to put in here then is the Sadler force. I love that. Force of Sadler, and that's going to be 35 degrees. Okay, are we okay on what I did there and why I drew that? So now we need to make sure everything goes left and right. So here are going to be the forces. Ready? We're going to have a force like this, which we call FGX. Okay, so that's going to be the force down the hill, pulling Ava down. When I'm trying to pull her, I go, oh my goodness, you're so heavy. Kidding around, that's why she's so heavy, because of the force of gravity, X. I'm also going to call this, straight down, called force of gravity Y. And I'll deal with those together with the force of gravity coming down together. So that's the force of her pushing down on the hill.
Oh, so is this kind of like components?
This is exactly like components. This is components. The other two ones I'm going to put on here, I'm going to put, I have a force of Sadler X, okay, FSX, and then I also have an FSY. So everyone see that? So everything, all of my components, I've taken relative to the hill. Are we okay on the logic there for that? Caleb, you're sort of seeing what's going on here? Now there's one thing I haven't drawn in here yet, and I'm going to draw it right now. What's the last thing that I have to do? Go ahead. Force of gravity. I'm going to do that in a new picture. I'm going to say FGX plus FGY equals the force of gravity. Okay, because that's what adds up. Can anyone here tell me how I calculate what the force of gravity is actually going to be? Go ahead.
M times G.
Yeah, so this is equal to M times G, which equals, what is it, 20 kilograms times 9.81, which is, oh, I can't do that in my head. Can somebody save me? 96.2. Okay. So what I'm saying is, if I add together FGX plus FGY, I'm going to get my force of gravity. So everyone see what I did there? Right, so I'm going to add those things together. Now, this is the tricky part. We got to get an angle in here. You have to remember this is what's really, this is what's really happening in real life. Okay, if I can spin this, hopefully. Force of gravity is going straight down, right, in real life. Okay, so I don't have to move that back, but if you take a look, that's really what's happening. It's going straight down. Let's move that back if we can. So what angle can we put in there?
90.
90 is a good one, but we need one more than 90. 90 is a good angle.
30,
30, which one's going to be 30?
the bottom one.
Now let's make sure I get this right, because I don't want to screw you guys up here. So that's now my hypotenuse. That's going to be 9. This one's going to be the 91 right here, actually.
Okay.
Right? So this, because technically this is going to be FGY. So I'm going to use actually this one as 60 up there. Okay? So I'm going to say this right here is 60 degrees, which makes this 130. Now please be brave and ask questions. Got what else?
Doesn't the normal force cancel out?
Yeah, the normal force we're going to talk about at the end. Okay, I'm going to leave that out. Because in this, there's a good question for the physics students. We have another force, another y force, which is me pulling upwards. So it doesn't necessarily cancel out gravity because there will be a normal force, but because if I'm pulling on this, what's something that's heavy? Let's pretend this is heavy. I'm trying to pull. There's a normal force that's working with me for it not to move, but it's still my fault. Are we okay on where that last triangle came from? Because that's the most difficult part here. If your physics teachers did it to you differently, that's fine, but I think for us math students, this is the clearest way to do it. Callan, are you somewhat understanding what's just happened there?
Somewhat, yeah.
Okay, well, we're going to do another one of these until you completely 100% understand it. So now I need to break this into components. This is 196.2. The nice thing about this is I gave a nice diagram that is a special triangle, right? We're going to actually use our calculators here if we can, though. Sine of 30 is equal to what? Back from the advanced function. What's sine of 30? Oh no. What's sine of 30? Okay, go ahead.
The force of gravity X.
Good.
For 196.2.
Close? Yes, okay. But just in general, yes, that's what it is. But what is sine of 30 equal, like in your calculator? 0.5, which is 1/2. So I can quickly, that is right. Sorry, I was out looking for a different question. So that's 88.1. Okay, so I can put this in here. This is 88.1 newtons. Okay? Does everyone get the idea there of where that came from? Okay, now we got to actually solve for FGY. We're going to say sine 60 equals FGY over 196.2. Can somebody tell me what FGY is, please?
169.
How much? A little louder? 169 point?
Wait, could you clarify the 88.1?
Yeah, did I add that up wrong?
Not sure.
So what I just did was sine 30 is 1/2, right? So I just did half of this. Well, that's 98.9. Whoops, is that 98.1? It is
Yeah.
98.1.
So
Thank
you
you.
just completely skipped the calculation.
I just skipped the calculation
Okay.
because, sorry. So this is 98.1 newtons, sorry about that. Force of gravity is 169.9. Okay. Are we sort of, this is like the first key step to these questions, breaking the gravity into components. Okay? Now this is the next thing. One more time, Brendan, when I say something is in equilibrium, what does that mean?
There's no net force.
There's no net force. Now, as far as components go, what that means is your x's cancel out to be 0, and your y's cancel out to be 0. In physics, they've also given you another one, which is called the normal force. Okay, so what I'm going to say is Fgx equals Fsx. Okay, those are going to be the same. So you got the idea, right? The forces to the left are the same as the forces to the right. And we'll say Fsy
And we just assume that.
plus Fn. Well, no, you don't just assume it. I told you that's the truth. Okay, so all my upward forces equal the same as my downward forces, and all my leftward forces equal to that. We assume?
Sorry.
So you said we just assume this is true. Well, no, we told you it was an equilibrium, so it has to be true. So as I said, here's the problem. Yeah.
Why isn't Fsy equal to FGY? Why is it constant?
Okay, good question. Because you don't necessarily know how much Like, let's say that gravity's 169 newtons, maybe only pulling the 70 newtons. You know what I mean? So I'm pulling upwards of 70 newtons, but there's still, whatever, 90 newtons left to go. Okay, so it's possible that it's not equal.
You don't have to do that to the GF?
What's that?
You don't have to.
No, because there's no other horizontal components, right? Okay, so how are we gonna find FGX? Stay with me here, guys, please. How are we gonna find FGX?
We did.
Well, we did. We already found it. What's FGX?
98.1.
98.1. So what I'm going to do is I'm going to use this triangle now. I know that this is 98.1. I need to find FX is all I need to do when I'm done. Okay? So because we're going to say, since this is true, therefore, FSX equals 98.1 newtons, we'll say whatever, 98.1 newtons. So here's my triangle, the last one. There's 35 degrees. This is 98.1, and this is x, and that's what I'll try that fx, and that's all I need to find. Okay, because I'm just trying to solve what force Mr. Sadler pulled back. That's all the question says. So we don't need to worry within normal force. We don't need to worry about FSY. We don't need to find any of that stuff. We just need to find the Sadler force. Okay. Teresa, I haven't picked on you yet today. Can you please use your powerful mathematics skills to tell me how to solve for FS? Please give me that triangle. Yeah. Sine law, I'm going to use a different one. I'm going to just use sine, not sine law, but yeah. So I'm going to say sine 35 degrees equals 98.1 over Fs. Therefore, Fs equals 98.1.
That doesn't work. Because
Naturally. You know what I love about you guys? This happens in every single calculus class, not just this one. You guys all sit silent and go, please someone give me an answer. Please, please, please. And I hear nothing. Nothing. It's like you guys aren't even here in this room. Please somebody give me an answer. And then I make one small mistake. I mix up sine and cos, and it's like a chorus of people anyway. All right, so thank you. That is cosine. That's correct. 98.1 divided by cos 35 is what?
119.75.
119.76. 119.76. So 0.8 then I'll call it. Therefore, Mr. Sadler pulls at 119.8 newtons. Now let's talk through this to make sure that we all get it, okay? Because this isn't an easy question. This is conceptually difficult. Yeah, go ahead, Brendan.
We don't need vectoring.
It would be up the hill is what it would be. The heading would be up the hill. It also says what force does it pull, but it would be up the hill is what you could say. Okay, so let's make sure we understand everything here. Let's go back here, okay? First step for these questions. Now, if you don't want, is you got to draw this minimum, okay? If you want to turn it sideways, it's easier to visualize sideways, but I'm a math teacher, so for me this works nicer. But if you want to keep it like this and solve it, okay? Once you have this, calculate your gravity, and then you need to draw the gravity diagram to break gravity into components. Yeah, go ahead.
I'm not understanding what third.
This one here?
Yeah.
Okay, so what I did was, I sort of used this original one, okay? Because what happened was we're going to have an FGX and the FGY adding together to get FG. And I knew this part across here is 30, which makes the angle at the top 60. So the angle between FGX and FG should be 60 degrees. Okay, the logic for that? And this one was your right angle here, right? Like following the same diagram. Okay. All right, so we get the gravity, break that into components, break the gravity into components. Then we said, and this is the key for this question, and this is called a free body diagram. It shows all the forces that are on here. That we have my gravity x here has to be equal to the Sadler x component. Okay, so then you can just go back to that and solve for the last one. I'm going to pause the video, and then I want everyone to put their heads on their desks for a moment, please. Because I want to find